Okay, what we're going to do now is we are going to talk about the idea of differentiability. We talked about it briefly in class, but I want to kind of go over it a little bit more thoroughly. So I'm going to kind of use some notes from a book and then an example. So the idea of differentiability. Differentiability means that a function has a derivative. Specifically, what it means is that when I'm looking at a derivative is a limit. And what I want the limit from the left and the limit from the right to be the same. And if we look at a function like here, like the absolute value function that has a corner here, at 0, as I come at this slope from the right-hand side, notice I have a positive slope. But as I come at it from the left-hand side to 0, I have a negative slope. So like the number that I'm looking at here is approaching, it's going to be a positive number. As I do it here, it's going to be a negative number in terms of slope. So what it's saying is at this point right here at that corner, it's not differentiable. It doesn't have a derivative, because if you kind of think about it, if I try to draw a tangent line there, I could draw an infinite number of tangent lines. It could be horizontal, could have any sort of skew to it at all. Same idea here. This is called a cusp. Same, either one. We don't use either word really that much, but corner cusp, again, as I come at this guy from the left, we're looking more negative. As I come at it from the right, we're looking more positive. So that's one idea of where we might not have differentiability. The other idea is where we might not have differentiability is where we have a vertical tangent line. So we look here at x equals 0. What we have is we technically have a tangent line that would have an undefined slope. And a slope of undefined means doesn't exist, so it's not differentiable here at that point. And then the last idea of differentiability is going to be jump. So there's a discontinuity here where if I think about it, the value of the slope here is going to give me, it's going to give me a 1 from the right, or the value is approaching 1 from the right, but it's approaching -1 from the left. So those two are not the same. So that wouldn't have a derivative at that point. So that's the idea of differentiability. So let me kind of walk you through an example of differentiability. So here's that problem we've seen a million times before. What we're going to do first is we're going to prove continuity, because the rule is this. If a function is differentiable, so if I told you that a function is differentiable, if I'm saying it is differentiable, that implies continuity. So in order to be differentiable, you have to be continuous. However, me saying something is continuous, me saying something has continuity, does not imply differentiability. Okay, so first thing we're going to do is try and prove that this guy's continuous. So the way we prove it's continuous, first thing we're going to do is we're going to be looking at it at 1, because that's kind of where our piecewise differs. We're going to look at, does f of 1 exist? F of 1 is going to equal a times 1 squared plus b times 1. That's going to equal a plus b. So that's my first one. The second thing is I need to look at the limit. The limit as x approaches 1 of f of x needs to exist. So what that means is I need to look at the limit from the left. I need to look at the limit from the right of f of x and see if those are the same. So from the right, it's what we've already done up top. That's going to be a plus b. It'd be a plus b. From the left, it's going to be using that 3 minus x. So what we're going to do is we're going to do 3 minus 1. That's going to equal 2. So here's where we're going to know, because here's the deal. For this limit to exist, these two guys have to equal one another. So what I have is I have the following equation. 2 equals a plus b. So I have one equation. So here's the problem. When I do this, this is my proof of continuity. So this is my proof of continuous. If you can do a proof of continuous, you can do a proof of differentiability, because honestly, differentiability is the following. What I am going to do to prove differentiability ability, I can spell. Okay, first thing I'm going to do is I'm going to take the derivative of that original function. So the derivative of that original function, using our rules that we know, the derivative of 3 minus x, derivative of a constant is 0, derivative of negative x is going to be -1 when x is less than 1. And then I'm going to use the power rule here. So it's going to be 2ax plus b when x is greater than 1. Okay, so here is the deal on this one. Only thing I need to check in this one is I only need to check number 2. Number 2 is that limit. So what I'm going to do is I'm going to look at the limit as x approaches 1 from the left of f of x. I'm going to look at the limit as x approaches 1 from the right of f of x. So in this case, again, I'm sorry, f prime of x. F prime of x, not f of x, f prime of x. So if I look at this guy from the left, the guy from the left is going to equal -1 because there's nowhere to plug in any value. If I'm looking at it from the right, it's going to be 2a times 1 plus b. So it's going to be 2a plus b. So for this limit to exist, because the limit needs to exist for differentiability, we're going to set 2a plus b equal to -1. And now what we have is we have 2 equations, 2 unknowns. What we can now do is we can actually do a system of equations, kind of like what we've done in the past in Algebra 1. So what I'm going to do in order to make this work is I'm going to go ahead and change the signs. I'm going to multiply everything here by -1. 2a minus a gives me a, b minus b gives me 0, -1 minus 2 is going to give me -3. So a is going to be -3. And then I can pick either one to figure out the other one. A plus b equals 2. Since I know a is -3, -3 plus b equals 2. Add 3 to both sides, b is going to equal 5. So if a equals -3, b equals 5. And what that's going to do is those values plugged in is going to make the limit here exist. So the limit as x approaches 1 of f prime of x is going to exist. And because the limit exists, I'm differentiable. So again, the rule is this. So we kind of review just so you have all of them in one place. The rules of continuity. To prove something is continuous, to prove that something is continuous, what you need to do are the following. You need to prove that f of c exists. And I'm looking for continuity at x equals c. First thing we're going to say is f of c exists. Number 2, we're going to look at the limit as x approaches c of f of x, and that has to exist. And remember, anytime we do a limit, it's actually 2 questions. I'm looking at it as it approaches c from the left. It has to equal the limit as x approaches c from the right of f of x. And then the third thing is f of c, my answer from 1, has to equal the limit as x approaches c of f of x. That's how we prove continuous. Okay. For differentiability, to be differentiable, differentiability at x equals c. The only thing we need to do is we need to prove that limit. The limit as x approaches c of f prime of x has to exist. In other words, the limit as x approaches c from the left of f prime of x has to equal the limit as x approaches c from the right of f prime of x. That's the only thing you have to prove for differentiability. So what you're going to do is you're going to take the derivative of your original function, just check the limit. And that's how we do differentiability. So that's kind of the last thing of this part of the unit. I wanted to go over so that you at least had some examples of it. We talked about it in class. We will talk about it in class today. And you now have another example. Please ask me if you have any questions. Thanks.